Hey, welcome to Jackdaw Patio. I'm Chris, and tonight I need to tell you about a number. One single number. It should be simple. It's supposed to measure how fast the universe is expanding right now. Astronomers have been chasing this number for almost 100 years. And here's the thing. They found it. Twice. They got two different answers, and neither one is wrong. That's not a riddle. That is the actual state of modern cosmology right now, in 2026. The Hubble constant, called H0, comes back as roughly 67 when you measure it one way, and roughly 73 when you measure it another way. Same universe, same physics, two clocks that refuse to agree. And the James Webb Space Telescope just confirmed that the disagreement is not a mistake. Now, if you've been hanging around the patio for a while, you know we're interested in moments like this. Moments when the tidy story cracks open and something stranger peeks through. Because here's what I find fascinating. This isn't just a problem for astrophysics. It's a question about what happens when you try to compress a living, evolving universe into a single symbol. Information theorists would call that a lossy compression. Mythic traditions would call it something else entirely. And if you've read any of the Eden hypothesis work, you might recognize the shape. One unified reality yielding different readings depending on which clock you use to observe it. Tonight, Lily, Charlie, and Dr. Vega are going to walk through this with you. We'll talk about what the Hubble tension actually is, why Webb removed the most comfortable escape hatch instead of solving the problem, what three very different explanations are still alive, and what it might mean, not just for cosmology, but for how we think about measurement, time, and whether a single number can ever carry the full weight of a cosmic history. 5 chapters, real science, real questions, and probably at least one moment where Dr. Vega says, "actually," and everyone groans. Grab your drink. The patio is open. Chapter 1. The Number That Should Not Disagree. Back in the late 1920s, Edwin Hubble sat at the Mount Wilson Observatory and realized something that changed everything. Distant galaxies were moving away from us, not randomly, systematically. The farther away they were, the faster they receded. The universe was expanding, and the rate of that expansion could be captured in a single constant, his constant, H0. For decades, pinning down that number was the holy grail of observational cosmology, and by the early 2000s, two independent methods had converged enough that most astronomers expected a tidy answer was right around the corner. They were wrong. Here's Lily, Charlie, and Dr. Vega.
Right, so let me set the scene because I think the story is actually more interesting than the number. You've got two completely different ways to measure how fast the universe is expanding. The first one looks backward, all the way back to the oldest light in the universe, the cosmic microwave background. That's the afterglow of the Big Bang, right? About 380,000 years after the beginning. You map that light. You feed it into your best model of the universe, and out pops a number. Roughly 67. Kilometers per second per megaparsec, if you want the units. But the number is what matters.
And then there's the other way, which is, if I'm understanding this right, you basically build a ladder.
A distance ladder, yeah. You start with stars you can measure really precisely. Cepheid variables. These pulsating stars whose brightness you can predict. And you use those to calibrate the brightness of supernovae, which are bright enough to see across enormous distances. Step by step, rung by rung, you work outward. And when you get to the top of that ladder and calculate the expansion rate, you get roughly 73.
So, 67 versus 73. That's what, about an 8% difference? That doesn't sound like it should keep anyone up at night.
Actually, it absolutely should, and here's why. Both measurements are now so precise that their error bars don't overlap. In statistical terms, we're looking at a discrepancy in the range of 4 to 5 sigma, depending on which data sets you combine. For context, 5 sigma is the threshold particle physicists use to claim a discovery. This isn't a rounding error. This is two extremely careful measurements of the same thing, returning answers that, statistically, should almost never both be right under the same model.
And that's the bit that gets me because, you know, in my work with ancient texts, you run into this all the time. Two cultures describing the same sky, the same floods, the same migrations, and the numbers never quite match. And usually that tells you more about the observers than about the thing being observed.
So, which measurement is wrong?
That's the question that's been burning through cosmology for about a decade now. And the uncomfortable answer, as of 2026, is possibly neither. The early universe measurement depends on a model. It assumes the standard cosmological model, called lambda CDM, is correct. If that model is slightly incomplete, the number it spits out could be slightly off. But the local measurement depends on a chain of calibrations, each of which introduces its own small uncertainties. For a while, the leading suspect was something called stellar crowding, the idea that Hubble Space Telescope images were blending multiple stars together, making Cepheids look brighter than they were, which would push the distance ladder's number too high.
And that's where Webb comes in?
Exactly. The James Webb Space Telescope has dramatically better infrared resolution. Adam Rees and the SHOES team used Webb to recheck over 1,000 Cepheids in multiple galaxies. The crowding hypothesis was rejected at 8 sigma. The old Hubble data was essentially correct. The ladder holds.
So Webb didn't solve the tension.
Webb removed the most comfortable escape hatch. The discrepancy is real, it's confirmed, and something has to give. Either the local ladder still has a subtle, systematic we haven't found, or the standard model of cosmology needs a revision. Or, and this is where it gets philosophically interesting, maybe the problem is with asking one number to carry two very different kinds of cosmic history.
I love that framing. Because that's not just physics, is it? Well, it's a bit like asking one word to hold two meanings that are close enough to confuse and different enough to conflict.
Like when my editor says, fine, and I have to figure out if it means acceptable or I'm furious with you.
Exactly like that, Charlie. Exactly like that.
Except in this case, the editor is the universe, and we're the ones who chose to compress all of cosmic expansion history into a single initial.
So if both measurements are right, or at least neither is obviously wrong, what does that actually tell us about the universe? Because I have a feeling the answer isn't going to be simple.
It's not, but it is structured. And to understand that structure, we need to talk about what these two methods are actually measuring. Because I'd argue they're not measuring the same thing at all.
Chapter 2. Two roots to one constant. So we've established the tension, 67 from the early universe, 73 from the local ladder. But what I want to do now is slow down and look at why these two methods might disagree, because the how of the measurement turns out to matter as much as the what. Different routes through the same cosmos, different clocks, and as we'll see, different assumptions baked into every step. Here's the crew.
Let me lay out the two routes more carefully, because the devil is genuinely in the details. Route 1, the cosmic microwave background. You take the oldest observable light in the universe, photons released when the plasma cooled enough for atoms to form, and you analyze the tiny temperature fluctuations in that light. Those fluctuations encode information about the density, composition, and geometry of the early universe. You then fit those patterns using lambda CDM, the standard cosmological model. And one of the parameters that falls out of that fit is H0. Planck gives you 67.4. The Atacama Cosmology Telescope, combined with data from the Dark Energy Spectroscopic Instrument, gives you 68.2. Tight, precise, and low.
And that's model dependent, right? You said that. So the number is only as good as the model.
Correct. And that's a critical point that often gets lost. The CMB doesn't have 67 stamped on it. You extract that number by assuming a specific cosmological framework. If there's physics happening before recombination that lambda CDM doesn't account for, say, an early burst of dark energy, that could shift the inferred value upward. Some researchers have shown that early dark energy models can push the CMB-derived value up to about 71, which would significantly reduce the tension.
So the early universe route is more of an interpretation of the data through a particular lens.
Every measurement is an interpretation through a lens. But yes, the CMB route has a particularly thick lens. The local ladder is more direct, but it has its own fragilities. You're chaining together multiple types of stellar distance indicators. You anchor to a galaxy with a known geometric distance, NGC 4258, whose distance is measured by water masers orbiting its central black hole. Then you calibrate Cepheid variables in that galaxy. Then you use those Cepheids to calibrate Type 1 supernovae in more distant galaxies. Each rung introduces uncertainty.
It's like those trust exercises where you fall backward and hope someone catches you. Except you're falling through 6 different pairs of arms.
That's a very Charlie way of putting it. And I have to say, it's rather good.
Broken clock, right?
Oh, speaking of clocks, that's rather the point, isn't it? These aren't just two methods. They're two different temporal perspectives. One is looking at the universe when it was 380,000 years old. The other is looking at it now, 13.8 billion years later. And they're assuming the expansion history between those two moments is smooth, predictable, well-behaved.
That's exactly the assumption that might be breaking. And here's where it gets interesting. There's a growing body of work using methods that don't depend on the sound horizon, the standard ruler that the CMB route relies on. Researchers from the DESI collaboration have measured H0 using the matter radiation equality scale instead, and they get about 70, right in the middle. Strong lensing time delays from the TD SOSMO collaboration give about 72, also in the middle, though with larger uncertainties.
So it's not really 67 versus 73 anymore. It's more like a spectrum.
A distribution. The tight low from CMB model fits, the tight high from the Cepheid supernova ladder, and a growing middle ground from independent methods, TRGB stars, JAGB stars, gravitational lensing, and eventually, gravitational wave standard sirens. The Hubble tension isn't a clean binary. It's a structured disagreement.
So it's less 2 universes and more 1 universe speaking in different dialects.
Oh, I love that. That's actually... Charlie, that's rather beautiful. It's like reading the same ancient tablet with 2 different regional scripts. Both true to the original, but the translation numbers don't quite line up until you understand which scribe's calendar was being used.
I have my moments.
And you remain stubbornly unaware of others.
What?
Nothing. Moving on.
So if the tension is real and structured, what are the actual suspects? What could be causing this?
3 main lanes, each with very different implications for physics. And one of them involves the possibility that our entire cosmic neighborhood might be a bit emptier than we thought.
Chapter 3. 3 suspects, no confession. This is the part of the episode where we lay out what might actually be causing the Hubble tension. And I want to be clear about something. Nobody knows yet. This is live science, unresolved, contested. What we're going to do is walk through the 3 main suspects the way an investigator would. Motive, opportunity, evidence. And I think you'll find that the least exciting explanation might be the most likely, which, on the patio at least, usually means there's something more interesting hiding underneath. Here's the crew.
Suspect number 1. Residual systematics in the local distance ladder. This is the conservative option. The idea is that somewhere in the chain from geometric anchors to Cepheids to supernovae, there's a calibration offset we haven't fully accounted for. Webb killed the crowding hypothesis, but that's not the only possible systematic. Metallicity corrections, dust extinction, anchor galaxy selection, supernova standardization. Each one is a potential source of small biases that could add up.
So the ladder might have a wobbly rung.
Possibly. And here's an interesting detail. Wendy Friedman's team, the Chicago Carnegie Hubble program, used Webb to measure distances using 3 different stellar indicators in the same galaxies. Cepheids gave them about 72. TRGB stars, tip of the red giant branch, gave them roughly 69.8. JAGB stars, a type of carbon star, gave them about 67.8. 3 methods, same telescope, same galaxies, 3 different answers.
That's not exactly reassuring.
It's actually extremely informative. It tells us that the local ladder is not monolithic. Different calibrators carry different systematics, The spread between 68 and 72 within the local ladder is almost as interesting as the gap between the local ladder and the CMB.
It's like interviewing three witnesses to the same event and getting three slightly different accounts. None of them is lying, but each one is filtering through their own perspective.
Nicely put. Suspect number 2, early universe, new physics. This is the theorist's favorite. The idea here is that something happened before recombination, before the CMB was released, that altered the size of the sound horizon. The sound horizon is the standard ruler that the CMB root uses to calibrate distances. If that ruler was actually shorter than lambda CDM predicts, the inferred expansion rate would be higher, closer to what the local ladder measures.
What kind of something?
The leading candidate is called early dark energy, a brief pulse of extra energy density that kicked in just before recombination and then faded away. Some researchers speculate that this could raise the CMB inferred value to about 71, cutting the tension roughly in half. It's still viable after the latest ACT and DESI data, though the parameter space is tighter than it was a few years ago. And there's a newer candidate, primordial magnetic fields. Full three-dimensional MHD simulations by Jadamczyk and colleagues suggest that magnetic fields in the early plasma could have altered how matter clumped during recombination, subtly changing the sound horizon.
So the universe might have had a magnetic hiccup at birth.
That's actually not a terrible way to describe it. A brief magnetic perturbation that left a subtle imprint on the CMB. It's testable, which is what makes it interesting. Mainstream cosmology doesn't treat this as established. It's a candidate, not a verdict. But it's a candidate with specific predictions.
And suspect 3?
Suspect 3, local structure. This is the one that sounds strange, but has a respectable body of work behind it. The idea is that our cosmic neighborhood, the region of space within about 1 billion light years of us, might be less dense than the cosmic average. A large void, sometimes called the KBC void. If we're sitting in an underdense region, matter would be flowing outward toward the denser walls. And that outflow would look, locally, like a faster expansion rate.
So, we might be living in a cosmic pothole.
Really? A cosmic underdensity, yes. And if that's the case, then the local ladder isn't measuring the global expansion rate. It's measuring a local peculiarity. The universe as a whole could be expanding at 67 or 68, while our neighborhood appears to expand faster because we're in a low-density region.
There's something rather poetic about that, isn't there? The idea that our view of the cosmos depends on where we're standing. That our neighborhood shapes what we see, even at the largest scales.
That's true of everything though, isn't it? You see what your position lets you see.
That's quite profound for a Saturday evening, Charlie.
Well, don't tell anyone. I have a reputation.
And then there's what the research pack calls the hybrid possibility. The least glamorous answer, a modest local systematic, plus modest model incompleteness, plus the recognition that compressing all of cosmic expansion into a single number was always going to strain something. Several small mismatches that happen to line up in H0.
The boring answer.
Yeah, often the most likely one. But even the boring answer has an interesting structure, because it suggests that the tension isn't about one thing being wrong. It's about a system reaching the limits of its own compression.
Are there any other suspects lurking out there?
One more worth mentioning, if only as a thought experiment. Some researchers speculate that the tension could be a symptom of gravity itself behaving differently at very low accelerations. An idea called modified Newtonian dynamics, or MON. Mainstream cosmology doesn't favor it, and the evidence for dark matter from other observations is strong. But it's the kind of question that keeps the field honest. What if the issue isn't the measurements or the model's contents, but the model's foundation?
And that's where this starts to feel like more than just astronomy, doesn't it? Because the idea of a single symbol carrying too much meaning, that's not just physics. That's how myths work. That's how language works. And it might be how consciousness works, too.
Chapter 4. One symbol, two histories. All right, this is where I want to bring in some of the Eden hypothesis framework. because I think it illuminates something important about what the Hubble tension is actually telling us. And I want to be clear, I'm not claiming the Eden hypothesis explains the Hubble tension. I'm saying the tension has a structure that the Eden framework was designed to describe. The structure of collapse. What happens when you try to compress something unified into something differentiated? Here's the crew.
So, Chris has been working on something called the Eden hypothesis. And the bit that's relevant here is this idea of collapse. Not quantum collapse specifically, though there are parallels, but collapse as a general pattern. You start with a unified field of possibilities, and through measurement, decision, experience, that field narrows into specific outcomes. And the key insight is that the narrowing itself introduces structure. It's not neutral. What you get depends on how you collapse.
Actually, I want to put a finer point on this, because I think it's worth being precise. The Eden framework introduces a function, lambda of t, that tracks the accumulated amount of collapse over time. In Chris's work, t was originally written as an external time parameter, but in a compatibility note published earlier this year, that parameter was reinterpreted as a relational clock, an internal variable, more in line with approaches like the Page-Wooters mechanism in quantum gravity. And that's directly relevant to the Hubble tension.
How so?
Because the two measurement routes we've been discussing are, in a structural sense, two different relational clocks. The CMB route uses recombination physics as its clock, the sound horizon, the plasma dynamics of the early universe. The local ladder uses stellar pulsation periods and supernova light curves as its clock. Both are legitimate. Both are measuring real physical processes, but they're indexing cosmic history through different subsystems. And when you try to compress both histories into one number, H0, you get a discrepancy. Not because one is wrong, but because one symbol is being asked to carry two different collapsed readings of the same underlying reality.
That's... okay, I want to make sure I'm tracking this. You're saying the Hubble tension might not be a problem with the measurements or the model. It might be a problem with the compression.
I'm saying it's consistent with that reading. Mainstream cosmology treats it as a measurement and model problem, and that's entirely reasonable. But the structural analogy is precise enough to be interesting, and it's testable. You can look at how the discrepancy behaves as you add more independent measurement routes. If it's a compression problem, you'd expect intermediate methods to cluster in the middle, which is what we're starting to see.
And that's what's happening with TRGB and JAGB and gravitational lensing. They're filling in the space between 67 and 73.
Exactly. The distribution is no longer bimodal, it's spreading. That's more consistent with a spectrum of observational perspectives than with two clean answers.
You know, this reminds me of something I've been reading about in Mesopotamian astronomy. The Babylonians had two different systems for tracking planetary motion, the System A and System B models. Both were accurate. Both made good predictions, but they used different mathematical structures. One used step functions, the other used zigzag functions. For centuries, scholars tried to figure out which one was right. And the answer turned out to be that they were both right. They were just compressing the same celestial motion through different computational schemes. The planet didn't change. The compression did.
So the universe has been doing this to astronomers for at least 3,000 years.
At least. The Greeks had their own version of it with epicycles. Every time you try to capture motion in a single formula, you run into the limits of the formula before you run into the limits of the motion.
And that's the deeper point. The Eden framework calls this the tension between unity and differentiation. The unified underlying reality, what Chris calls the Eden state, can be accessed through multiple observational pathways. Each pathway introduces its own collapse dynamics, its own accumulated lambda. And if you're not aware that your measurement is also a collapse, you'll mistake a perspective-dependent feature for a property of the universe itself.
It's what the framework calls the serpent of time, isn't it? That curvature winding through the unity field, leaving behind these differentiated readings. Two measurements, two bends in the serpent, two different footprints of the same passage.
But is there a concrete test for this? Like, not philosophically, can you actually measure whether the compression is the problem?
Yes, and this is where I want to be careful, because I take this stuff seriously. The specific measurable proxy is the behavior of H0 estimates as a function of method independence. If the tension is driven by genuine new physics, say early dark energy, then all methods should eventually converge on a revised value once the model is corrected. If it's a compression effect, you'd expect a persistent spread that narrows only as you move to methods that make fewer model assumptions, like gravitational wave standard sirens, which are essentially model-free. The next generation of gravitational wave detectors will be decisive.
So we're waiting for the universe to speak in a language that doesn't require us to choose a clock first.
That's a beautiful way to put it. And it's not mystical, it's operational. Standard sirens give you a direct measurement of the expansion rate without needing a sound horizon, without needing a distance ladder, without needing a cosmological model. They measure the universe's expansion using the fabric of space-time itself, gravitational waves from merging neutron stars and black holes.
And when those come in?
If they confirm 73, the model is almost certainly incomplete. If they confirm 67, the latter has a systematic, "we missed." If they land at 70, which is where my gut says they will, we're going to have to rethink what H0 actually means.
Or what we thought it was measuring.
So what does all of this actually mean? Not for cosmologists. For people sitting on a patio drinking something cold, looking up at the sky, wondering what's out there. What do we do with a universe that gives two answers to the same question?
Chapter 5. One Universe in Two Dialects. This is the chapter where we step back and ask the question that matters most on the patio. So what? Why should this matter to someone who isn't an astrophysicist? And I think the answer has to do with something we all recognize. The experience of looking at the same situation from two angles and seeing two different truths. Not two opinions, two truths, and having to hold both of them at the same time without collapsing into false certainty about either one. Here's the crew.
I keep coming back to this idea that the Hubble tension is a kind of mirror. Not of the universe, of us, of how we know things. Because we want one answer, one clean number, one truth. And the universe keeps saying, it's more complicated than that. Not contradictory, complicated.
And that's uncomfortable, isn't it? I mean, I've spent my career in photojournalism, and one of the hardest things I ever had to learn was that the same event, photographed from a different angle, with different light, at a different moment, it tells a different story. Not a false story, a different one. And you have to hold space for both versions being true.
That's lovely, Charlie. Really.
What, I can't be thoughtful?
No, you can. It's just, when you are, it's rather disarming.
I'm going to resist the urge to comment on the concept of Charlie being disarming, and instead point out something about the science that I think matters for this conversation. The Hubble tension may ultimately teach cosmology a lesson about what constants are. We call H0 a constant, but it's not constant in the way that the speed of light is constant. It's a parameter that summarizes the current expansion rate. But the current expansion rate is the result of 14 billion years of cosmic history. It carries the imprint of everything that has happened. Dark matter, dark energy, radiation, structure formation. One number. 14 billion years of history compressed into it. Maybe the tension is telling us that compression has reached its limit.
And that connects to something I think about a lot in mythology. Every myth is a compression. The story of Eden is a compression of the entire human experience of becoming self-aware, of moving from unity into distinction, from a garden into a world. And the power of the myth is in the compression. But the danger is when you forget that it is a compression, when you start treating the symbol as the thing itself.
Like treating H0 as the expansion rate rather than as a summary of the expansion rate.
Exactly. The map and the territory. And what the Hubble tension might be showing us is that our map, lambda CDM with its 6 parameters, is a brilliant map, but it's not the territory. The territory has more structure than 6 numbers can hold.
Do you think there's a resolution coming? Or is this one of those questions that just stays open?
Some resolution is almost certainly coming in the next 5 to 10 years. The Euclid Space Telescope is mapping the dark universe right now. The Nancy Grace Roman Telescope launches soon. More gravitational wave events will accumulate. DESI is still collecting data. We're going to have so many independent measurements that the picture will sharpen whether we want it to or not. But, and this is where I'll offer a thought experiment rather than a claim, I suspect the resolution won't be a single aha moment. It'll be a gradual realization that H0, as we've been using it, needs to be decomposed into something richer. Not one number, but a function. Not one constant, but a story.
A story. The astrophysicist wants a story.
Well, every equation is a story. Some of them are just very compressed.
And some of them apparently are too compressed.
You know, there's something oddly comforting about all of this. The idea that the universe is more than any single number can hold. That even cosmologists, people who literally study everything, have to sit with uncertainty. Have to hold two answers at the same time.
It's the oldest human posture, really. Sitting with mystery. Not running from it, not pretending you've solved it, just sitting with it. On a patio, if you're lucky. With friends.
And a drink.
And a drink. Yes.
And for the record, if anyone is looking for a measurable test of whether the tension is a compression artifact versus genuine new physics, watch the standard sirens. Gravitational wave events from LIGO and the next generation detectors give us an expansion rate measurement that bypasses every rung of every ladder and every cosmological model. When those sample sizes grow large enough, which should happen within this decade, we'll know. That's not speculation. That's a prediction with a timeline.
So the universe will eventually answer the question, just not in the language we originally asked it in.
That might be the most accurate thing anyone has said all evening.
Cheers to that.
Cheers, Charlie.
And just to be clear, we should note that none of us are cosmologists. Well, I'm an astrophysicist, but this isn't my primary lane. Everything we've discussed tonight is based on published research and publicly available data. But viewers should always check the original papers and talk to working cosmologists before treating any of this as settled. Science moves, numbers update. That's the whole point.
All right, I hope you enjoyed that as much as we did. Let me give you the quick summary. Tonight we talked about the Hubble tension, the fact that two independent methods for measuring the expansion rate of the universe give two persistently different answers. 67 from the cosmic microwave background, 73 from the local distance ladder. We learned that the James Webb Space Telescope confirmed the local ladder isn't making a simple mistake. It eliminated the leading systematic suspect at 8 sigma. We walked through 3 live explanations: residual calibration issues in the distance ladder, early universe new physics like early dark energy or primordial magnetic fields, and the possibility that our local cosmic neighborhood is less dense than average. We saw that the tension is no longer a clean binary. It's a structured spectrum with multiple intermediate measurements clustering around 70, and we explored what all of this might mean through the lens of the Eden hypothesis. Not as an answer to the tension, but as a framework for understanding its shape. One symbol carrying 2 collapsed histories, 2 relational clocks indexing the same universe through different subsystems. The idea that the tension might be less about a broken measurement and more about the limits of compression, trying to pack 14 billion years of cosmic evolution into a single number. The concrete test to watch: gravitational wave standard sirens, model-free, ladder-free, direct. When the sample sizes grow large enough, and they will, we'll know whether H0 is hiding one story or 2. If any of this sparked something for you, a question, a connection, a memory of looking up and wondering, that's what the patio is for. Come sit with us. We've got a chair. You can find the full episode on Substack and YouTube. The audio version is on Spotify. We're on Reddit for discussion and on X at Jackdaw Patio. If you like this, share it with someone who'd enjoy it. Like, follow, subscribe, all the things. Every share, every comment, Every new person who pulls up a chair makes the conversation richer. This has been Jackdaw Patio. The patio is always open. See you next time.